For living organisms, memory is an incredibly important part of survival. After all, memory is what allows living creatures to learn from experience and adapt to their environment. But have you ever heard that even a cold, rigid, lifeless piece of metal can actually have a memory? You can bend it, twist it, and completely deform it, yet the moment it's heated to a certain temperature, it snaps right back to its original shape. A strange metal that almost seems alive, as if it remembers the shape it once had and restores itself back to the way it was before. And even its name sounds mysterious somehow, shape memory alloy. In this video, we're going to explore how shape memory alloys were first discovered, what kind of mechanism allows them to remember their original shape, and where they're being used today. Alright then, let's get started. The paperclip you're looking at right now is actually made from a shape memory alloy. As you can see, you can bend it, twist it, and completely deform it. But the moment heat is applied, something incredible happens. It slowly snaps right back into its original paperclip shape. Just a second ago, it was completely crumpled up, and now it looks as if nothing had ever happened. It almost feels like the metal has a mind of its own, remembering the shape it originally had. So then, when exactly was this strange material discovered, and who created it? The unique properties of shape memory alloys were first truly realized in the mid-20th century with the development of an alloy called nitinol in the United States. Interestingly, this breakthrough happened almost completely by accident. In 1959, the US Naval Ordnance Laboratory, or NOL, was working on a project to develop military-grade alloys that could maintain high strength and durability, even under extreme temperatures. At the time, the project was being led by a materials scientist named William J. Buehler. Exactly how Buehler carried out his research isn't fully documented, but based on my own experience working with materials, I think we can make a fairly reasonable guess about how the research may have unfolded. And the approach I'm about to describe is actually still a very common way of designing new materials and alloys today. First, you'd probably think something like this. If we want an alloy that can survive high temperatures, we should start with metals that already hold up well under heat. And one of the most obvious choices for that would be titanium. As I mentioned in a previous video, titanium is relatively lightweight while still maintaining excellent strength at high temperatures. Of course, if you only care about high temperature performance, there are even stronger options out there, like tungsten. But tungsten has one major problem. It's incredibly dense and extremely heavy, and considering that the original goal was to develop military materials for extreme environments, lightweight titanium would have looked far more attractive than something as heavy as tungsten. Next up, corrosion resistance. Just surviving high temperatures isn't enough. Real materials also need to withstand oxidation and corrosion in harsh environments. So what kind of element could be added to improve that? One of the best candidates would be nickel. As I mentioned before in my Devil's Metal episode, nickel is commonly used in alloys to improve both high temperature performance and corrosion resistance. Naturally, this leads to a pretty simple idea. What if we combine titanium and nickel? Maybe that combination could create an alloy that's lightweight, strong at high temperatures, and resistant to corrosion all at the same time. And it's very possible that William Buehler started his experiments with a similar line of thinking, and that's how the nickel-titanium alloy was born. But unfortunately, the alloy didn't perform as well as they had hoped. Its high temperature strength and corrosion resistance weren't impressive enough to fully satisfy the original goal of creating a military-grade high-temperature material. But then, during one laboratory meeting, something unexpected happened. A researcher named David Muzzy picked up a heavily crumpled strip of nickel-titanium alloy and casually held a cigarette lighter underneath it. And then, right in front of everyone, the metal suddenly snapped right back to its original shape. The entire room was stunned. That moment would eventually become one of the most famous stories in the history of shape memory alloys. Even after the nickel-titanium alloy had been severely bent and deformed, heating it above a certain temperature caused it to return to its original shape as if nothing had happened. Although shape memory behavior had been observed in limited form since the 1930s, this was the first time the phenomenon had been demonstrated so dramatically in a metallic alloy. It marked the beginning of commercially viable shape memory alloys. The research team combined the alloy's two main elements, nickel and titanium, with the name of their laboratory, the Naval Ordnance Laboratory, and that's how the name nitinol was born. So how exactly does a shape memory alloy return to its original shape? To explain this as simply as possible, picture a stack of boxes balanced right on the edge of a cliff. When the boxes are perfectly aligned, their center of gravity is stable and everything sits in a balanced and comfortable state. Shape memory alloys work in a very similar way. When the alloy is first manufactured, the atoms inside the metal settle into their most stable arrangement, just like those neatly stacked boxes. But when the metal is forcefully bent or twisted, the atoms are pushed slightly out of alignment, leaving the internal structure in a very unstable state. It's almost like those boxes near the edge of the cliff have become crooked and uneven, barely managing to stay balanced without falling over. The problem is that at low temperatures, the atoms don't have enough energy to move around freely. So even though the structure is unstable, the atoms simply remain stuck in place. But the moment heat is applied, the situation changes. The atoms gain energy from the heat and begin moving again. Naturally, they start returning to the arrangement that was originally the most stable. And because the overall shape of the metal is ultimately determined by the arrangement of its atoms, once the atoms move back to their original positions, the bent metal itself also returns to its original shape. And nitinol, the nickel-titanium alloy, is one of the best-known examples where this phenomenon appears most clearly. Interestingly, the temperature at which nitinol returns to its original shape actually changes depending on how much nickel is added to the alloy. In general, the higher the nickel content becomes, the lower the temperature at which the shape memory effect appears. And by carefully controlling the manufacturing and processing methods, engineers can even design nitinol to activate anywhere from around -20 degrees Celsius to roughly 110 degrees Celsius. But shape memory alloys don't just recover their shape when heat is applied. These materials also have an extremely strong tendency to spring back to their original form, even without temperature changes. For example, even an ordinary metal spring can be compressed or bent by hand and still bounce back into its original shape. That property is what we call elasticity, but shape memory alloys like nitinol show this effect much more dramatically than ordinary metals. They can bend much further without breaking and almost behave like rubber, constantly trying to return to their original shape. This unique property is called superelasticity. So then, where exactly are these fascinating properties of shape memory alloys actually being used? Interestingly, even though nitinol was originally developed for military applications, today it's used far more actively in the medical field. One of the most well-known examples is the medical stent. A stent is a tiny mesh tube used to reopen narrowed or blocked blood vessels. Nitinol is especially useful for this because it can be compressed into a very small shape before entering the body, and once inside the blood vessel, it naturally expands again in response to body temperature. But nitinol isn't used in stents simply because of the shape memory effect alone. Our blood vessels are constantly moving, bending and flexing, and thanks to nitinol's incredible superelasticity, it can endure repeated deformation without breaking easily. Even after being squeezed or bent, it strongly tries to return to its original shape. This combination of shape memory behavior and superelasticity gives nitinol major advantages in medical applications, especially for peripheral vascular stents used in highly flexible areas like the arms and legs, as well as delicate neurovascular devices designed for the extremely narrow and complex blood vessels in the brain. Another major application is orthodontic treatment. Nitinol is also used in the arch wires attached to teeth during braces treatment. It plays an especially important role during the early stages of treatment when the teeth are still severely misaligned. As the wire continuously tries to return to its original shape, it generates a gentle and steady force that slowly guides the teeth into better alignment over time. And beyond that, nitinol is used in many other types of medical devices as well. But shape memory alloys aren't limited to medicine. They're also used in a variety of advanced industries, especially in aerospace engineering. For example, some satellites use shape memory alloys in systems that deploy folded antennas or structures once they reach space. Satellites are usually launched with large solar panels or antennas folded tightly inside a rocket. Once the satellite reaches orbit, those structures need to unfold. But in space, heavy systems like motors or hydraulic devices can become a major disadvantage. Shape memory alloys offer a much simpler solution. With nothing more than temperature changes, the material can return to its original shape and automatically unfold the structure. In other words, a tiny piece of metal can effectively act like a motor and generate movement on its own. Because of these unique properties, shape memory alloys have found their way into a wide range of technologies, from industrial valves and switches to aerospace systems and even artificial muscles for next-generation robots. But what's really interesting is that shape memory alloys can also be found surprisingly close to us in everyday life. One of the most common examples is eyeglass frames. Nitinol frames can be bent dramatically and still return to their original shape. Because of this, they're highly resistant to deformation and far less likely to break. So when you see products advertised as nearly unbreakable glasses, there's a good chance that shape memory alloys like nitinol are being used inside them. Today, we explored nitinol, one of the most fascinating shape memory alloys out there. Even though it's already being used across a wide range of industries, researchers are still finding new ways to apply it in even more fields. And honestly, considering its incredible properties like shape memory behavior and superelasticity, it probably wouldn't be an exaggeration to say that the potential applications of shape memory alloys are almost limitless. It's actually pretty exciting to imagine what kinds of technologies this material could be used in next. If you have any fun or creative ideas for future applications of shape memory alloys, feel free to leave them in the comments below. That's it for today's video. I'll be back with another fascinating scientific story in the next one. Thanks for watching. This has been Dr. Sai Vera.